Hi, welcome to the August 5th meeting of the Kubernetes VMware User Group. On the agenda for today's meeting is a deep dive into the Kube-Vip load balancer for Kubernetes. At the meeting a month ago, some of you, I think, were there, some of you perhaps not, but that meeting was recorded and is up on YouTube. And there are some notes for it in the agenda notes doc that I put in the chat. A month ago, we did kind of a broad coverage of load balancers for Kubernetes. And at the end of the meeting, we did an audience poll, probably not scientific because of sample bias, but Kube-Vip came out as a leader in terms of what people in this group who attended the meeting are using now. So we thought we'd invite Dan to do a deep dive into Kube-Vip. It's an interesting project, and it looks like some people are already familiar enough with it to be using it, but maybe others not. But hey, you can't beat going right to the originator of the project and looking at the GitHub stats. I think he's still doing a lot of the, what do they call it, chopping wood and carrying water. So, Dan, I'll turn it over to you. Maybe you can start with, we tried to do a summary of Kube-Vip last month, but maybe we didn't do it justice. So if you want to just start with an intro, because we've also got some newcomers here.
Sure.
And then we'll go into deeper dive into whatever you want. I think you already got some questions on chat, and maybe if anybody's got any, please start. You can type them into chat or wait till Dan's done talking and do them verbally. So over to you.
Okay, not a problem. Thank you very much for inviting me and having me be part of the VMware User Group. So I guess a little bit of background. I am currently at Equinix Metal, where I am leading a team of engineers who are focused on a lot of kind of Kubernetes things, cluster API for bare metal, and a bunch of other kind of automation tools all around bare metal and things like that. But prior to Equinix Metal, or what was Packet, I was at VMware, where I was there as part of the Heptio acquisition, where I was running kind of field engineering in EMEA. And it was kind of at Heptio where I had a focus of bare metal Kubernetes clusters. So a lot of the work I was doing whilst I was at Heptio was kind of architectural best practices around getting Kubernetes stood up on bare metal platforms. And through that, I kind of hit a number of issues that I thought maybe I could automate, and maybe, you know, there's a solution here that can be made, and out of, you know, kind of that, where kind of Kube-Vip came from. So I've got like a bunch of slides that I've put together. I can kind of rattle through those quite quickly. If you do have any questions, then please just ask me them as I'm kind of going through the slides, and we can, you know, we can kind of bounce backwards and forwards and things like that. So where did it actually come from? So as I mentioned, when I was at Heptio, I was doing a lot of bare metal provisioning. And I effectively wrote a bunch of software to automate the provisioning of Kubernetes on bare metal. And this all kind of came about because one customer that I was working with flew over to go work with them. They kind of walked me into a room, told me what they wanted, and then just disappeared. And they effectively just asked me to build basically a Kubernetes cloud on their bare metal servers that acted and felt like they'd be able to do things in AWS, which was quite bonkers at the time. But effectively at the end of like a 2-week stint with them, I'd written loads of shell scripts and this, that, and the other to automate all of this work. And out of that, I kind of realized that maybe there's another project that I could do. So effectively, I wrote a project called Plunder, which was a bare metal provisioning for Kubernetes. And the next step for that, really, I thought of was using cluster API on top of this project for bare metal provisioning. And it is kind of there where I started to hit issues. So if we look at kind of Kubernetes architecture, it has the control plane, and then it has a number of workers that will sit and communicate with that that are communicated to via the control plane. And if you lose that control plane, then effectively workloads will carry on running, but you can no longer make changes or manage or monitor or have any real idea in terms of what's actually happening inside your Kubernetes control plane. So when basically deploying a HA Kubernetes cluster, there's a number of components that you kind of need in order to have a highly available control plane. You need obviously more than one control plane node, but then you also need things like a clustering technology, which will expose a which will expose a additional IP address, which is effectively like a floating IP address. And then you'll need the capability of load balancing between all of the nodes that are in the actual control plane. And at the moment, you can do this today, or you could do it then, sorry, but you needed a number of tools in order to do that. So you could use things like Keep Alive D and HA Proxy and Nginx and things like that. The problem that I really had there was that they really did not fit very well into the cluster API model. You had 3 then sets of configs to manage. We had a VIP technology, we had a load balancing technology, and then we had kind of the management of Kubernetes and the control plane and things like that. So it's kind of that and trying to automate that, which is where I decided that there's probably a better way to do this. And I also realized that in automating that, I also could use that same technology to provide load balancer services for actually inside the Kubernetes cluster as well. So using the technologies that I'd put together for creating a highly available control plane with load balancing, I could use that same technology inside the Kubernetes cluster and expose that same functionality for your services whilst running things inside a Kubernetes cluster. So what is the architecture of Kubernetes, Kube-Vip itself? Originally, I looked at using Raft. However, it turned out that it was quite unstable in terms of the way that kind of cluster API does a lot of the node upgrades and things like that. Effectively, you require that odd number of nodes in order to do things. However, when we would remove a node as part of the upgrade process, so typically with cluster API, you'd have 3 nodes that are version 1.20. You would remove a node and add in a new node that's version 1.21. Raft would basically just explode at that point when that 3rd node was removed. And with no leader in the cluster at that point, there was no VIP. With no VIP, there was no way to access the cluster. So whilst it worked the first time you kind of had it up and running, the upgrade procedure was very unreliable with Raft. So I opted to use the technology that comes out of the box with Kubernetes. So there is an election API that the Kubernetes API exposes. It's called the Leader Election API, and it's used by a variety of different things inside the Kubernetes API and some of the various other control plane components make use of it and things like that. The way that it works is that effectively a number of pods or effectively anything that's used in the Kubernetes API can say to the Kubernetes API, I want to hold a lease that's called this, we can call a lease Kube-Vip, for instance. And we can have a number of pods or bits of code saying, I want to hold this lease. The API will select one of those requests and say that you actually have that lease. So at that point, that pod in our instance has been told it has the lease. And once it has the lease, it can then say, right, I'm now in charge. This is where the VIP should be. This is where traffic should come into the cluster. This is important for ARP. So there's a number of technologies that Kube-Vip uses in order to expose addresses to the outside world. ARP, BGP, we're looking at OSPF. There's some others that we can possibly look at as well. But ARP and BGP are typically the most common that we're seeing at the moment with Kube-Vip. And ARP effectively is how a new IP address will expose itself on a network. So effectively, ARP will, we can apply an address to a node. We can then use ARP, which is effectively a lookup table. So it effectively says to the network, if you want to get to this IP address, it is at this MAC address. So effectively, if you want to send traffic to this IP address, then data should be sent to this hardware address on the network. And we use ARP to broadcast and update the network as to where something actually is. So this is important as with a floating IP address, when that IP address moves over due to node failure or upgrades or anything like that, or a new leader election, when that new leader is elected, it can do that ARP broadcast. The network then knows that the IP address has moved, so traffic should then be sent to that node where the IP address has actually happened. 1 second. So as mentioned, when we do that broadcast, we're effectively telling the network which hardware to send traffic to. The other technology that we use, there's one other thing about ARP that's important as well. Only one node should be doing ARP broadcasts saying that it has that IP address. That's why we need leader election with ARP. This is because a network gets very confused when multiple pieces of hardware share the same IP address. You will effectively end up with broken traffic and things like that. So only the leader should be doing the ARP broadcast. And when it does the ARP broadcast, the network then knows to send traffic for that IP address only to that one host. BGP is slightly different. So BGP is a layer 3 routing protocol. What it effectively allows a node or nodes to do is tell the routers in the facility that if they want to send traffic to an IP address, then they should route that traffic through my IP address. So we can see on this diagram here, we've got four hosts, .20 to .23. Effectively with BGP, what we do is we would say, if you want to send traffic to the VIP, then send traffic to .20, and .20 then will take care of sending the rest of that traffic onwards to where the VIP actually lives. So how does that actually work? So in this example, .21 is now doing BGP advertising. .21 will tell the top of rack switch or the router that if for traffic to get to that 10.0.2.5 address, it should route the traffic through itself. So what that actually means is that when an external node wants to access that 10.x address, the router will send that traffic to .21, and that traffic will then be passed on to the VIP, which is 10.0.2.5. Now, the one good thing about BGP is multiple nodes can advertise at the same time. What that means is that our external host, the MacBook at the top that is trying to go to 10.0.2.5, the traffic will go to the router, and the router then will forward that to one of the hosts that are advertising. So we get additional load balancing from the top of rack router itself. So ARP versus BGP. ARP doesn't require any special equipment. It's just layer 2. A switch has these ARP tables. So anything that does that ARP update, in your home network, for instance, that will just work. With BGP, you need to have some software running that understands BGP peering and things like that, or you need an expensive router or top of rack switch that supports BGP functionality. Negative for ARP poisoning can disrupt a network. We negate that by using cluster leader election. If we didn't have that and we had multiple nodes all doing that, then we would easily end up kind of losing traffic on the network. BGP can mandate authentication, so we can effectively say only nodes with this password and MD5 hash are allowed to advertise those routes, so we can protect who's advertising those sorts of routes. Some switches, and I don't think it's an issue inside VMware with DV switches and things like that, but some switches and some hardware network don't like a node advertising an address that it's not aware of. So some Cisco switches will block this out of the box. BGP, because it's layer 3, may require firewall rules enabling. And then ARP is good for small edge networks and smallish network segments, whereas BGP is fantastic for huge networks with tens of thousands of addresses and routes and things like that that you'd like to advertise. So I've kind of quickly rattled through that. I'll just quickly check the chat. If there's anything in here? Raft is a true pleasure to work with. That's in speech marks, so I'm assuming that's an ironic pleasure. Okay, Paxos for life, fantastic. So I'll quickly kind of go through the installation. As I mentioned, if anybody does have any questions, then please kind of let me know as I'm kind of stepping through this, but I'll kind of go through this bit quite quickly as well. So how do we actually deploy and run Kube-Vip? Kube-Vip runs inside of Kubernetes. It needs to run inside of Kubernetes because it makes use of things like the leader election. So in order to do that, it needs to be able to speak to the API server and things like that. The two most common deployment methods are static pods or Daemonset, but both of those have quirks that you may need to be aware of in terms of deploying Kube-Vip. So static pods, for those that don't know, a static pod is a pod that is not managed by Kubernetes itself. A static pod is a pod that is managed by the kubelet on the node itself. So you can drop a manifest into a location on a node, and the kubelet will be in charge of maintaining that pod actually up and running. The reason why this is important is with KubeADM, there's a kind of a chicken and egg scenario that I was hitting in order of getting Kube-Vip up and running. The problem that we have is that when we do a KubeADM init, and this is how things like Cluster API vSphere work and things like that, we do a KubeADM init with a control plane IP address. KubeADM init basically will bring up the cluster, wait for the components to start, and the last thing that it will do, which defines whether it's a success or failure, is try and access the API server through that control plane IP address. Now, if Kube-Vip hasn't come up, or whatever technology that you're using for load balancing hasn't come up, and KubeADM init can't hit that IP address and thus the API server, it will fail. And at which point you've basically got like a half stood up cluster, but no credentials to do anything with it and things like that. So we need to be able to deploy into a cluster before there is actually a fully formed cluster. And we do this with static pods. So the way that we do that is we put in the etcd manifests folder our manifest for Kube-Vip. So what that actually means is that as KubeADM init, because KubeADM init will basically put in the manifests folder a number of other static pods. So things like the API server and etcd and a few other things, they're actually all static pods that run on nodes as well. KubeADM init will put all of those manifests in there, where the Kube-Vip manifest will also exist. Those components will all come up together. So the API server will start, etcd will start, but Kube-Vip will also start along with it. What that means is that the Vip will spring into life. As the API server starts, Kube-Vip can then speak to the API server and do that leader election. And on the first node, it's the first thing that's actually up. It's the only thing asking for that lease. So it, by default, will get that lease and become the leader in the cluster, at which point it will start advertising the Vip to the outside world. KubeADM in its final step will speak to that IP address. And hey, presto, we now have our first node of the cluster actually up and running. The next step then is to join all of the other the nodes to the cluster. and add in the static pods on those other control plane nodes. So that's effectively how it stands itself up. With a daemon set, it's much easier. But with a daemon set, we can't do kubeadm in it. So for a daemon set, you would do that when looking at things like K3S. That has a different way of bringing up nodes and things like that. It doesn't have that check for being able to speak to the control plane VIP at that time. So with this, we can effectively do K3S server and standard path first node. We do the TLS SAN for our VIP. All that means is that we sign our API server with that VIP address at that time. And then we drop in our daemon set for Kube-Vip, at which point then we can add in all of our additional K3S control plane nodes. The daemon sets by default for Kube-Vip are all tainted to just run on the control plane nodes in this example. So that daemon set will just spread across the control plane nodes, at which point you have HA automagically across all of those nodes. So that effectively gets us a highly available Kubernetes control plane. So we have Kube-Vip either running as a daemon set or static pods on all of our control plane nodes. One of the nodes from an ARP perspective will be the leader through leader election. In the event that that node goes through upgrade or node failure or anything like that, a new leader election will take place, at which point the network will be updated so that to get to that VIP, send traffic, in this instance, to control plane node number 3. With BGP, all 3 of the control plane nodes will effectively be advertising to the routers or top of rack switches that they have the VIP. And in the case that any of these nodes fails for whatever reason, they will stop advertising to the top of rack switch. So here we can see we're trying to speak to the VIP. If we lose one, it will stop advertising that route to the top of rack switch or router, at which point that route will disappear from the router and traffic will only be sent to nodes 2 and 3 in this example. So that kind of covers the HA control part of it in terms of how it all works. As you can see, it's quite simplistic in how it works. There's even when I kind of wrote the thing for the first time, I was surprised at, I guess to a degree, the simplicity of the bits that kind of were put together. But I kind of did this to begin with, and then as I've mentioned, I kind of realized that same technology that we just kind of showed for the HA control plane could also be used for Kubernetes services as well. So before I kind of jump into this, is there any questions? Okay, so this
actually just a quick question, Dan.
Sure.
Regarding regarding like using BGP if you're using cluster API, where nodes get DHCP addresses. How do you deal, have you dealt with using BGP and cluster API, and how would you update BGP peers? Because that seems like the BGP would only work in static IP clusters. Almost.
So the way that, so effectively for BGP to work, let me just pop back here. So I've not shown on here, but we would have a daemon set or a static manifest which would have the BGP peers in it. So effectively the BGP peers in this example would be, normally there'd be more than one router here, but there's just one router in this diagram. Those top of rack switches are going to be relatively static. You don't tend to replace your routers on a regular basis. So those router peers would be in the manifest, whether a daemon set or a static pod. The one thing that does need to be unique is the server ID of the BGP client. So the way that we do that is as the static pod or the daemon set manifest, we can specify a bit of information in the Kube-Vip manifest where it will look up the IP address on an interface and it will use that as the unique ID in order to peer with. So effectively, in order for peering to work, node 1, node 2, and node 3 need this unique server ID to differentiate themselves to the router to which they're peering. And we can use that IP address as kind of the peering mechanism to work. And it will look that up as Kube-Vip starts. It will then connect to all of the BGP peers in its config. And then as we advertise things, it will notify those top of rack switches. So it would work. The manifest would be different, but it would work the same as ARP in cluster API. There's a lot of kind of things that. Oh, sorry.
There's no need to update like what because it's coming. The BGP peer on the top of rack would be though the DHCP IP of the control plane node. There's no need to configure the BGP peers then anytime that a control plane node would change its IP on the top of rack switch so that it can set the two-way BGP peering.
No, so effectively as a node, so if the control plane node's using DHCP or things like that, the nodes turn on, get a IP address, the process for joining them to the control plane or would happen. It would use that DHCP address as its server ID, and then just start peering with the top of rack switch. If a node dies or anything like that, it would just stop peering, and that would be the end of it.
Okay.
So it would all be very it would be dynamic as things spring into life. They would start that peering, but Kube-Vip would look up the address on startup and then use that in order to peer with the top of rack switch.
Okay. Cool.
Okay, cool. So I believe this was actually a question from Steve, which was, what is the relation of the cloud provider and Kube-Vip? So luckily this kind of covers it. There's two components that are required for load balancers to work inside a Kubernetes cluster. The first is a CCM or a cloud controller manager, and then something to actually do the networking, whether that's an F5 top of rack switch or Kube-Vip inside your Kubernetes cluster and things like that. So, kind of what do they do? What's the relation here? So a CCM is effectively the secret source for your infrastructure. If your infrastructure, if you're AWS, then your CCM or your cloud provider, its role is effectively being able to speak to the AWS infrastructure and get information that is relevant to the Kubernetes cluster. So if you do a kubectl expose inside AWS, the CCM inside Amazon, for instance, its role is to get you an ELB address and write that into the Kubernetes API object. There's a CCM for VMware. I don't know too much about it because I've not looked at it, but I'm presuming if you do a kubectl expose and you're using things like NSX, it will more than likely speak to the NSX API, inform it of the fact that there's an expose happening, and then it will get that API, get that IP address from NSX and write that into the Kubernetes object. So a CCM effectively is the translation layer between a Kubernetes cluster and the infrastructure that it's actually running on. Now with on-prem, edge, your home environment and things like that, nobody wants to write a CCM for everybody's home lab. That would be a nightmare, and they're not the easiest of things to write. So for Kube-Vip, I've effectively written as much of a general purpose CCM as possible. And the CCM, so the CCM that's been written for Kube-Vip effectively just manages simple IPAM. So with the Kube-Vip cloud provider, you can effectively say, here are 10 IP addresses on my network. If somebody does a kubectl expose, get me an IP address from that range that I've told you about. and then it will effectively use that as an IP address, assign that to the service, and then we can make use of that. So it's a very simple CCM. As I've mentioned, its main role is being able to give it a pool of IP addresses. It will then, kind of manage the lifecycle of those IP addresses for Kube-Vip to then advertise to the outside world. So how does the CCM actually work? So if we do a kubectl expose of in this example, Nginx, if we actually look at the spec of the service, we can see here that there is a load balancer IP part of the spec of the service. That is where the CCM makes a change. This is really one of the only things that the CCM should do. So the CCM doesn't load balance. It doesn't do anything other than get you some information that is relevant to your infrastructure and then update the service with that bit of information. So for instance, I've done that expose. The CCM hasn't done anything quite yet. We can see that the load balancer IP address hasn't been updated. When the CCM springs into life, it will look in its pool. It will take an IP address from that pool, and it's the spec.loadBalancer IP that it will update. And then that is it. That is the job of the CCM. The CCM then goes back to sleep and has no more work to do. So one second. Okay, yep. So how does Kube-Vip actually work from that point onwards? So we have a service. It's a service of type load balancer. The CCM has applied an IP address to it, which is great. But if I do a kubectl get service at this point, it will still say pending. I can look at the spec and I can see that the load balancer IP has been updated. So my service has an IP address, but it's still pending. And I'll show you why that is in a second. So in this example, we've got Kube-Vip deployed as a Daemonset running on a select number of workers. So we've used some selectors to say where Kube-Vip should actually be running. All of these Kube-Vip pods that are running as a Daemonset, they have what's known as a watcher, which is a Kubernetes API technology which can watch particular object types inside the Kubernetes API server. So Kube-Vip is watching for services type load balancer, and it will watch for a spec.loadBalancer IP address changing. So when a load balancer IP address has been allocated via the CCM, we now know that the service is ready to send to the outside world, at which point we will either use ARP or BGP to advertise to the rest of the network that send your traffic to me in order to get to this service. And the other thing that Kube-Vip will do in order to make this service go from pending to actually up and running is it will also update the service object inside the Kubernetes API. It will update the status of it with the load balancer IP address. Only once the status has been updated of the service is it reflected inside Kubernetes as ready to run. So only once Kube-Vip is actually broadcasting to the network and it's told the service that it's doing that, only then will it reflect inside, when you do a kubectl get service, that it's actually up and running. This is probably slightly less relevant, but for some edge deployments, there has been a request to effectively have both everything all running in the same place. So effectively what that means is we can run Kube-Vip on just the control plane nodes, providing high availability with ARP or BGP to the network. And also those three nodes with the Kube-Vip pods running will also take care of load balancing for the cluster. So we could have no workers. We could effectively remove the taint from the control planes. We could then have workloads running next to the API server and things like that, but also get load balancing, also get HA and things like that, which this was a request for edge deployments and things like that. So some other things that were asked for, DHCP load balancers. So on small or edge networks, we might not want to care about the IP ranges, or we may not want to have to deal with those sorts of things. We can leverage whatever devices are on that network that are using DHCP to give us an IP address for our service. So how that works is that if we do a kubectl expose, we need to specify that the load balancer IP address is 0.0.0.0, which is effectively an erroneous IP address. However, we're allowed to enter this into the service. And what effectively that means is that Kube-Vip will see this 0.0.0 IP address, at which point it will go down a slightly different code path, where Kube-Vip will create a pseudo network adapter on the host. It will then broadcast on the network that I need an additional IP address from the DHCP server, at which point whatever DHCP server that's actually running will give Kube-Vip an IP address, at which point Kube-Vip will update the service spec and status with that new IP address, and then do ARP to tell the rest of the network that if you want to send traffic, I've just got this IP address, send it to me via that new IP address. So we can effectively leverage things that already exist on the network to give us service IP addresses on there. So some additional things that are actually coming, additional control plane load balancing. So looking at IPVS to load balance actually inside the control plane between all of the nodes, regardless of which one is the voted leader. Distributed ARP load balancers. So this is nearly complete. The way that this is going to work is at the moment, you can have as many pods running Kube-Vip. However, only the pod that has won the leader election is sending the ARP broadcast. So effectively, only that node is receiving traffic for either a HA, if it's HA you're using Kube-Vip for, or if it's load balancing a service, then it's all going to that one node that has been elected leader. Now, we can distribute this by effectively using multiple leader elections. The way that this would work is that when you do a kubectl expose, we will do an additional leader election within all of the Kube-Vip pods for that particular service. And whoever wins that leader election, that is then in charge of that one service. So effectively, every service that somebody does an expose for, there's a new leader election between all the Kube-Vip pods, and that will allow us to distribute services between different nodes that are all part of the Kube-Vip Daemonset or static pods and things like that. So it's effectively one of the few ways that we can kind of share the load when using ARP. We've done a number of BGP enhancements to allow next hop exposing. So depending on your environment, you could do a kubectl expose and expose directly to the internet and have traffic route all the way in to your services. You can kind of see this in places like Equinix Metal. So inside Equinix Metal, we run Kube-Vip. We run Kube-Vip with the Equinix Metal CCM. The Equinix Metal CCM effectively will get you an IP address from the Equinix Metal API. Kube-Vip will then basically be able to do BGP to tell Equinix Metal routers that go out to the outside world to send traffic in to that address. And then additional things, I mentioned OSPF, improved observability and monitoring, and working on improving the documentation. This was a little bit old, so Kube-Vip has been accepted into the CNCF sandbox. So it is now officially a CNCF project. And as of yesterday, my talk on Kube-Vip was accepted at KubeCon. So if I'm allowed to go, if the USA will allow people from GB in, I will be at KubeCon to answer people's questions about Kube-Vip as well. So there's a lot of excitement going on around it at the moment. Some additional questions we have here. What are the minimal realistic resource requirements of running Kube-Vip at an edge location? It can run on a single CPU core and typically requires less than 100 megabytes of memory. It's very lightweight. It only starts a couple of Go routines, one of which is a Go routine that will watch services if you have that enabled, for instance. ARP broadcasts are effectively writing a few bytes to the network, and then that's it. So it is incredibly lightweight, mainly due to basically the simplistic technologies that it makes use of. What are the limits of using the Kube-Vip load balancer? So effectively, the limits really are how you've deployed Kube-Vip. As I mentioned, if you're using ARP, then at the moment, only the Kube-Vip node, which has been elected leader, will be receiving traffic. That is a bottleneck, but it is effectively, at the moment, until I've finished my PR for distributed ARP, it is the only way of broadcasting on a layer 2 network where traffic should go in that kind of use case. With BGP, however, BGP powers the internet. You're effectively down to as many routes as can be added to a router. So it's highly unlikely that you're going to hit any issues when using BGP with even the biggest clusters with Kube-Vip. When deploying, what are considerations, points of failure, and best practices for high availability? So, I mean, high availability effectively comes out of the box. It was what I originally designed Kube-Vip for. So, as I mentioned, it uses the Kubernetes API server in order to do that high availability when using ARP. When using BGP, then everything is highly available until you lose all of the control plane nodes. So, Kube-Vip will carry on running as long as the API server's there, or as long as there is enough control plane nodes to actually keep the lights on. Are there any metrics exposed which could be useful for troubleshooting layer 4 issues? Not at the moment, but a colleague, Gianluca, implemented most of the observability hooks in there. Work still needs to be done in order to do that, but the basic parts of observability are all there. The rest of it's just not been fully implemented yet. However, it does have a lot of logging that it can generate. So for troubleshooting, typically anything from a layer 4 perspective is all going to come out through to the logs. If ARP broadcasts are failing, then you will be made aware of it. And if BGP peering is failing, then that will all be reported as errors as well. You mentioned hybrid mode was mainly for edge deployments. Currently, we use MethyLB to do our load balancing on VMware. Would you view Kube-Vip in hybrid mode as a viable production replacement for that? Depends on the size of the cluster that you're actually running. So I probably, if it's not really an edge cluster, as in if you've got like a number of worker nodes, I probably would recommend leaving Kube-Vip to do the HA and then effectively just swapping out, or if you want to replace MetalLB, there's no reason to replace MetalLB if it's doing what it needs you to do. But if you were, just deploy Kube-Vip as a Daemonset and have that running on a select number of nodes as part of the cluster. I suppose one of the things that differentiates MetalLB from Kube-Vip is that MetalLB has dependencies on config maps and some of the things that make it are kind of quite highly tied together. Kube-Vip doesn't tie itself to any config maps or anything like that. It ties itself to Kubernetes API objects, which means Equinix Metal could write a CCM that spoke to their API and just updated the services. Kube-Vip will only care about Kubernetes API objects. It doesn't need to try and parse a config map or anything like that. It just watches those primitives. So anybody could write their own CCM that looks at their own network, does their own sorts of things. As long as that updates the API objects within Kubernetes, so updates the services object, then Kube-Vip will just take care of then exposing that to the outside world. So I think that's it for me. Are there any further questions? I know I've kind of rattled on quite a lot through all of that, but I hope that all made sense.
Yeah, it does, Dan. I'm just checking the chat. It looks like we've caught up, and I've been trying to transcribe some of that over into the notes, but we're caught up there now. But anybody else want to have a go, or since we've got Dan here, any other open-ended things you'd like to discuss in this whole field of high availability or scaling? And I did drop a link to that KubeCon session. The KubeCon session currently is slated to be hybrid, both physical in Los Angeles as well as online. So regardless of what happens for COVID-related travel or whatever, everyone should be able to catch that online.
My fingers are fully crossed that we all get to be there, but we shall see.
Yeah. Yeah, I live in Los Angeles, so if
quite the commute.
It doesn't get canceled as a physical event, I'm 100% on board with being there physically. And I'm hoping that if any other members of the group manage to show up physically, we perhaps have a social gathering to get together. It was something that Robert had arranged to happen in the ill-fated KubeCon Europe of 2020, but maybe finally we'll pull this off.
Absolutely. I suppose before everybody departs, is there anything that people are seeing a need for to a certain degree from kind of on-prem load balancing and things like that? Okay.
Well, I'll throw something out just to, I don't know if this is a question per se, but in addition to this group, I happen to be associated with the Kubernetes IoT Edge working group. And one of the things, obviously for Edge, you've already covered that this is suitable for an on-prem deployment and has low resource usage. But one thing that routinely comes up there is the ability to deploy this air-gapped. So
yes,
managing to be able to bootstrap something up when you don't have internet access or that access is intermittent is a big issue for those. The other one is being able to tolerate, even if you're normally connected to the internet, being able to tolerate a scenario where the power goes out at a site, you restart from a power outage, and during the restart, you don't have internet outage, but you'd like to recover operation at the closest approximation to what you were at before the unfortunate event happened. It sounds like there's enough here to manage to, so that this is suitable for that. But if you have any experience or additional comments you want to make on how well that fits in those edge scenarios.
Yeah. So from an architectural perspective, as in ARM and things like that, from an edge perspective, Kube-Vip is built for all of the different kind of ARM devices. It's a number of people run it on Raspberry Pis and things like that. Alex Ellis has been doing a bunch of stuff with Kube-Vip for a variety of different testing that he's always kind of doing with his things like that. Kube-Vip doesn't require any internet access. So as long as the image is either pre-installed in the container runtime cache, or you have a local registry, as long as that image is actually present, then the runtime will start it. In the event of a power outage, if you're using KubeADM to stand up your cluster and static pods, then upon resuming the nodes, so you power everything back on again, your control plane nodes, when they start, they will power on. Kubelet will start. Kubelet will start everything that's in the manifests folder. So etcd, API server, scheduler. It will also find that Kube-Vip manifest. So Kube-Vip will come up along with all of those components. As all of those components all come back together, the control plane will reconverge. The workers will be able to speak back to the control plane IP address and things like that. So given the simplistic deployment nature of it, it will just come up with all of the control plane components, regardless of what's happened in the data center.
Okay, as a time check, we've got 5 minutes left. If anybody has any last minute nominations for discussion in this area or something related, or final questions.
All I can say is I've actually been running Kube-Vip on ESXi on ARM, and it works awesome. So I have it running on a cluster, running on ESXi on a Raspberry Pi cluster in my house, which is very fun and works well.
That's fantastic to hear. It's one of the weird problems. I'm slowly starting to get more and more feedback, but for quite some time, I didn't really know who, if anybody, was actually kind of using Kube-Vip. And it's cropping up in kind of all manner of kind of quite crazy places at the moment. So it's nice to get feedback that it's kind of doing what it's meant to do.
Yeah, you missed it.
It definitely is.
Yeah. We had an audience poll. Now, granted, you can see that this is a limited number, but there definitely are people using it. And I think it's MetalLB got an early start for people using it at Edge, but I think people are discovering other things out there and maybe challenges to trying to use MetalLB for these Edge applications. So the trend is that I think Kube-Vip usage is growing.
And Miles just pointed out it does UPnP as well, which is a bit of a it's a bit of a funny one, but effectively for edge networks, if you do a kubectl expose and you have UPnP enabled on your home network, for instance, so your home router, your Netgear router or whatever, it will actually do a UPnP update to your router, which effectively will do port forwarding from the outside world into your service. So if I was to do a kubectl expose Nginx port 6000 or something or other like that, I would suddenly find that my router is now exposing port 6000 to the outside world. And if somebody connects to the IP address that my ISP has given me on that port, traffic will then come in to my Kubernetes cluster, and I'll be able to access the pods underneath that service as well. Which is
I'll have to check that out. I have some things in my home lab used. I know UP&P, the only thing in my household it's used for is media servers, like music and things, but that's nice to hear. I don't know what the business use cases are for that, but there's a big one for home entertainment.
Absolutely, yeah. I mean, it's generally used for kind of like Xboxes, so kind of things work and whatnot. But yeah, I just kind of thought that might be a fun use case. So it's just something amusing to implement, really. It's not really I don't think there's a production use case for it.
It's good for Minecraft servers running on
oh, good point.
Kubernetes.
Okay, there we go. Fantastic.
Nice.
Yeah, there's a few open source music servers too, where you can put your MP3 collection up on a home server and then play it on your mobile phones and things as you move around the world.
Fantastic.
Okay, well, thanks, Dan. That was a great presentation, and I'm looking forward to your KubeCon talk as well. Before we go, if anybody in this group has nominations for a topic for next month's user group meeting, Miles and myself are all ears. We like suggestions for topics that people are interested in rather than having to guess and go get speakers. So please challenge us. You're welcome to just throw it out now in the last minute of this meeting, or leave us a note in the Slack channel for this user group. So have we gotten to talk on Antria before? I don't think we have in this group. We can. What we're trying to do here, this group is chartered by the CNCF to be focused on running Kubernetes on VMware infrastructure. Technically, Antria is associated with VMware, but it's not real. It doesn't have a super solid tie to vSphere infrastructure. It runs fine there, but it runs fine, or it should run fine anywhere else as well. But if it's an interest, we could perhaps open it up and cover generalized CNIs that are appropriate for using on vSphere. That's probably all of them, but if it's a topic of interest, yeah, we could cover that. We might even have a couple people I see in the attendees who could talk about that if we have any volunteers here. Otherwise, I can go out and look for people on the Antria project. The things that do relate to running on vSphere, I think, are, one of the issues with running, this applies to both storage plugins and network plugins, is there's often a strong interest in somehow tying the Kubernetes objects to the vSphere objects if you get involved with troubleshooting or trying to apply policies or resource allocations. And that would actually be an interesting topic. I'll have to see who I can get to address that, because maybe this is one of these situations where there's room for improvement in pulling that kind of thing off, of mapping the Kubernetes objects over to the vSphere objects. But yeah, okay, let's see what we can do there for getting a speaker for next month. With that said, we're about 1 minute over, so I'm going to call this meeting to a close, but thanks everybody for attending. Go definitely check out Dan's talk at KubeCon. Also, this user group, Miles and I, will have a talk at KubeCon, and we're going to be talking about using GPU resources from Kubernetes workloads when Kubernetes is hosted on vSphere. So we've got a talk green-lighted for KubeCon on that subject as well. And if that interests you, the applications for GPUs might be machine learning or something else, we will have a talk put together for KubeCon coming up in October. So once again, thanks everybody for attending.